Today let's talk about a series RL circuit. The RL stands for a resistor inductor. Here you see a picture of a series RL circuit. I've got my 13 millihenry inductor and I have a 2.7 k ohm resistor. The frequency is 33 kilohertz and this is all connected to a 10 volt source. Now the very first thing I'm going to do is calculate X sub L. The formula for X sub L is 2 pi times the frequency times the inductance. Now using my calculator, I'll type in 2 times pi, which I use 3.14, times the frequency, which is 33,000 hertz, times the inductance, which is 13 millihenries. And I come up with 2,694.12 ohms. Next, I calculate the impedance of the circuit. The impedance of the circuit, the formula for that is the square root of the resistance squared plus the inductive reactance squared. So using my calculator, I'll type in the resistance, which is 2.7 k ohms, that's 2700 ohms, then I square it, then I go plus the inductive reactance, which is 2,694.12 ohms, square that, equals, and then I take the square root of that answer, and I come up with 3,814.22 ohms. Now what we've just done in the circuit is the resistance of the circuit was given, that was 2.7 k ohms. The inductor opposes the current, and the inductor was a 13 millihenry inductor. We calculated the inductive reactance and found that X of L equaled 2694 ohms of resistance. So what we do is we calculate the total opposition to current in the circuit by taking the resistance in the circuit and the inductive reactance in the circuit. This gives us the total opposition in the circuit to current, which is the impedance. And we use this formula here. After I find the total opposition of current in the circuit, I can then find the total current in the circuit, I sub T. The formula for current is the source voltage divided by the total opposition to current, which is the impedance. So I take the source voltage, which is 10 volts, divided by the impedance, which is 3,814.22 ohms, and I get 2.62 milliamps of current. After calculating the total current, I can calculate the phase angle of the circuit. The formula for phase angle is the inverse tangent of the inductive reactance divided by the resistance of the circuit. So using my calculator, I'll take the inductive reactance, which is 2,694.12 ohms. I divide it by the resistance, which is 2,700 ohms, equals. Then I'll take the inverse tangent, and I get 44.94 degrees. Next, I'm going to calculate the voltage drop across the resistor. Now the formula for voltage drop is total current times the resistance. So the total current I found was 2.62 milliamps times the resistance in the circuit, which is 2.7 k ohms, and I get 7.07 volts. Next, I will calculate the the voltage drop across the inductor in the circuit. Ohm's law for voltage is total current times the inductive reactance. So I'll take the total current, which is 2.62 milliamps, times the inductive reactance, which is 2,694.12 ohms, and I get a voltage drop of 7.06 volts. Now I want to talk about the phasor diagram for just a moment. If I had a purely resistive circuit, then the total current phasor, the voltage drop across the resistor phasor, and the source voltage phasor would all be in phase. This would be for a purely resistive circuit. What we have, though, is an inductive circuit. With an inductive circuit, the total current and the voltage drop across the resistor are going to be in phase with each other. In fact, the total current and the voltage drop across the resistance are always in phase with each other. Those two phasors will never be out of phase with each other. However, the voltage drop across the inductor will always be in front of the total current and the voltage drop across the resistor by 90 degrees. Always. The voltage drop across the inductor always leads the total current and the voltage drop across the resistor by 90 degrees. Those three phasors never changes. What does change is the source voltage phasor. And what causes this change is the inductor. The source voltage phasor is actually going to phase shift in front of the total current by a certain amount, which is phase angle theta. The inductor is what causes this phase shift. If we look back, you remember we calculated a phase angle theta, and we calculated it to be 44.94 degrees. So we would say that the source voltage leads the total current by 44.94 degrees. Or you could say the total current lags the source voltage by 44.94 degrees. You're saying the same thing, just two different ways. So remember that an inductor causes the source voltage to phase shift in front of the total current by phase angle theta. And that's what we're working out with these calculations. The next thing we're going to talk about is power. And the first thing I'm going to mention is the power triangle. This is the power triangle. On the X horizontal, we always measure watts. If you remember, watts is electrical energy that is converted into heat and light energy. This is actually work that's being done. VARs, which stands for volt ampere reactive, this is actually a measure of energy that is stored in an inductor's magnetic field during a portion of the sine wave and then returned to the energy source during the other portion of the sine wave. So this is actually a measure of energy that is being shuttled back and forth between the inductor's magnetic field and the energy source. So this is wasted energy. This energy does no work. The hypotenuse is called the volt amps, and this is the combination of watts and VARs. Now we calculate these values by using the power formula I squared R. The wattage is called true power, and I'm going to use I squared R for that. If you remember, the current we calculated to be 2.62 milliamps. So I'll take 2.62 milliamps and square it and multiply it by the resistance, which was 2.7 k ohms. And I get 18.53 milliwatts. Next, I'm going to calculate the reactive power. Remember, the reactive power is the energy that's being shuttled back and forth between the inductor's magnetic field and the energy source. Same formula. I'm going to take the I squared, but this time instead of the resistance, since this is dealing with the inductor, I'm going to use X sub L. The current was 2.62 milliamps. I'll square it. I'll multiply it by X of L, which is 2,694.12 ohms. And I get 18.49 millivars. And then lastly, we're going to calculate the apparent power. And remember, the apparent power measured in volt amps is the combination of the watts and the vars. Same formula, I squared, but now this time the combination of the watts and the volt amp reactives is the volt amps, which is the impedance. So when I take the current and square it, 2.62 milliamps times Z, which is 3,814.22 ohms, I get 26.18 millivolt amps. So what I'll do is I'll draw my power triangle with watts being on the X horizontal, and we calculated this to be 18.53 milliwatts. The vars is the Y vertical, and this we calculated to be 18.49 millivars. Then the hypotenuse is the volt amps, which we calculated to be 26.18 millivolt amps. And the last thing we need to talk about is power factor. The formula for power factor is the cosine of angle theta. Angle theta was 44.94 degrees. So using my calculator, I'll type in 44.94 degrees, and then I simply hit the cosine key. And I come up with 0.71. If I convert that to a percentage by moving the decimal point 2 places, I get 71%. And the power factor, I believe anything above 70%, 70-75% is a pretty decent power factor. So the system is probably running about the best that it can. And that is how you work a series RL circuit.